Okay, good morning, everyone. Welcome to another session of SDA skills today. Uh, so today's topic is backtracking. We have discussed this topic before, a couple of sessions before, and today I tried to pick different problems for today. Um, but before we get started with the problems for today, just to give an brief understanding of uh, the approach. So backtracking is a brute force approach where you try to find all the solutions possible. Um, in general, brute force is that like you find all the possible solutions and pick what you want, right? So backtracking is a brute force kind of a solution, uh, except that it has some constraints based on which you don't choose some of the options, um, and those are called like bonding functions and stuff. So in general, it's like you use this backtracking approach, like where you're trying to find a solution, like you have a couple of options to choose, and like you choose one of the options and go uh, try to get to the solution, and based on the constraints you don't get to the solution. So then you have to come back and pick the other options that you had. Like you went in one direction to get to the solution, but based on the constraints based on the constraints of the bonding functions, you are not able to get to the solution. So you backtrack and go back and pick the other options to try and find all the solutions. So that's basically the idea. um, so I think there are different ways people choose to try and solve these problems. One way where I found one approach where I found it was easy to understand was using the state space trees, where we can track the decisions and try to find the solutions. So I'll try that for one or two problems today, and see like if that makes sense for everybody. Uh, so before I start on it, any other ideas on where do you guys think that backtracking uh, backtracking approach is useful? Sure. Um, yeah, anything you can think of. Like I think like we kind of pretty much like covered like the basic idea. So
So
just
how
want to
about
see that.
so Naga? How about the permutation combination problems where you have to uh, you pick an element and then try to make a combination out of it,
Mm-hmm.
and then you remove an element and then you make a combination with a different element.
Yeah.
So are we going to cover that as well today?
Today I picked like mostly combinations kind of problems, but
Mhm.
the idea is like I believe, yeah, that's right actually. So even there, the idea is again like we pick a number and then remove and come back, right? So again, it's also kind of choosing an option in one direction and then going back. So it's similar.
Mhm.
I have combination problems in today's session, so we can
Yeah,
see.
yeah.
I haven't picked.
Because that kind of applies to graph problem also, right? Like we take based on the problem we take certain route and then we come back and we like going to a particular path we identify that it's not the right way, and then when we remove the nodes and take a different direction. So it's
That,
that's also a similar category.
yep, that's right. I specifically did not choose those grab problems or like the finding the path in the maze and uh, n queens problems today, because those are the kind of problems where it kind when you look at it, it becomes quite obvious that you took take the path, come back and stuff, right? So I didn't
Mhm.
choose those things. Today's problems are like specifically on the combinations kind of model.
Okay. Okay.
Let's see how this gets applied.
Got it. Okay. Yeah.
Yeah.
I didn't get to see
But
the
I think I
problem, so
agree
just
with
yeah.
Sumit Naga. Yeah, I mean, so basically, backtracking is nothing but a variation of DFS, right? You are going deep to the decision trees, and at certain point, you are thinking, hey, this
Mhm.
decision, what I'm going to take, it doesn't make sense for me, right?
Mhm.
And exactly same thing is happening in the maze, right? I mean, behind the scene, it's kind of a DFS, and if you abstract DFS, it's a recursion, right?
Yeah. Yeah.
And backtracking is just like another, like a fancy term, I would say, like how it is, modeled in most of the computer science term. But it's
Yeah.
basically, whatever the decision you take, remove that it and
Mhm.
go to the next decision in the looping, right? Try something else.
Correct.
Yeah, it applies agreed with most of the problems like graph also.
Yeah.
You go in a DFS and then you are removing from stack or queue and you are then adding something, right? I mean, internally we are doing the backtrack, correct?
Yes,
Yes.
exactly. I mean,
Internally, I think the back.
exactly. I just calling them out just to give that understanding that all the problems are same as Sujit mentioned, but since it's a different category, we just get confused sometime and look at it a different perspective. But they are all the similar problems and have a similar solution of DFS and then pruning.
Yeah. That's right.
Yeah,
Yeah.
exactly. Yeah, I mean, if you see the problem, they looks different. Like what my understanding, right? You see the subset, you see the combination, you see the permutations. They all
Yeah.
look different, but behind the scene, they are based on underlying same concepts, right?
Yes,
How you manipulate them, just little bit different. Patterns are similar.
yes,
Yeah.
exactly.
Yeah, to add to what Sujit said, like this one, backtracking, actually can be used in topological sort also, right? If we
Yeah,
go,
that's
yeah, the
true.
DFS way, yeah. So that
It's
is one
all
more.
interrelated, right?
Right, right, right.
If you think about dynamic programming, it's basically casting, right? In the recursion, you put in cast, but the terms are created in such a way, right? To
So
to
yeah, I mean, it is very helpful, right? You can solve
yeah,
it many problems using that.
yep.
Yeah.
Yeah, yeah. And just to stress out, like I mean, I just wanted to share my experience that I have seen lately that in interviews has been around these topics a lot. uh, the backtracking topics in terms of permutation combination problem, graph problem, or topological sort combinations, stuff like that.
Mhm. Yeah. I was not able to relate backtracking to these subsets and combination problems a lot. So that's the reason I picked those problems for today. And let's see how that goes.
Hmm.
Um,
Okay.
uh, Before I start, any other ideas like that? That was a good observation from every one of you. So okay, so it looks like are you guys able to uh, access the handout? Looks like some of you are not able to.
I am.
Uh,
Yes.
yes, no. Okay,
Yes,
okay, 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 cool. So let me share and get started with it. So I picked two problems from lead code and one I just wanted to try something else. So I picked it from Tech Delight or something. Um, so let's get started with, uh, okay, I'm trying to share my screen. Okay, so this is the handout that I shared. So this is a problem that I just wanted to try something out of lead codes. I picked it. That's an interesting problem. I was trying to solve it, and I found like it is a little bit different. The thinking is a little bit different. Let's get to it later. For now, let's start with one simple problem, and we can also look at the state space tree. What I was talking about to try and understand how to apply this backtracking, and how the depth first search, like Sumit was mentioning, how the depth first search is used for it. So it's a simple, straightforward. It's a straightforward problem where you're given an array of integers. You need to find all the subsets. So, and here again, we are given like these numbers are distinct integers. So we can also look at like if it repeats, that's an extension to this problem. We can also look at it once we are done with this one. And one more condition that is given is like solution set must not contain duplicate subsets. That means like you are given 1, 2, in your solution, you cannot have like 1, 3. Once you have 1, 3, you cannot have 3, 1, and like those kind of duplicate sets. But otherwise, what's required is try and find all the subsets of this given set of numbers. So basically, like empty, one number, two number subsets, and every subset of this one can become a subset problem. So I'll 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 show like I did draw a state space tree for this one. So I'll show how it is, and then discuss that. So are you guys clear on the question? I believe this is like an most common question, so I'm not asking anybody, but I believe this is clear, right? Any questions on the problem? Just finding the subsets of a given set. So here, like, we don't have any bounding conditions at all. Bounding conditions here is like, make sure you are using the numbers within the set. That's it. That's the only bounding condition that we have. So let me share my state space tree. Okay, so this is the state space tree I was talking about. So this is one way of looking at this backtracking problems, where it makes it easy on like how you take the decisions, backtrack, and pick the next options that you have taken. So this is one good way I found of representing the backtracking problems. So you're given this 1, 2, 3 as the numbers. Now you are required to find all the subsets of the given set of numbers. So the subsets become like, you can choose like different ways to get the subsets. One is like uh, empty, you don't take anything, that's one. And you can pick 1, 2, 3 different numbers, and then you can pick like 1, 2 different kinds of things. So how do you choose those things using this tree, right? So once you are given 1, 2, 3, the first option that you have is like empty, right? And then you have an option to choose either 0, 1, or 2. So like I said, it's kind of a depth first way of looking at it. So you choose uh, 1 here, and then once you choose 1, so you had like 0, 1, 2, 3, 0. Sorry, I've also put indexes just to keep a track, but you had an option to choose 1, 2, or 3. You chose 1 here, and then you sorry, I had this diagram, but if I had drawn this, it would have been made much sense. But let's say like I'm going, I'll take you through the path. So you have chosen 1 here, and then you had 2 options to choose, either 2 or 3. So you go in one direction where you choose 2 only, and then you only have one option to choose, which is 3. So you chose like 1, 2, 3. And now once you get to 1, 2, 3, you are bounded by the function saying that you have selected all the numbers that you have. Now you backtrack. So when you say backtrack, what you say is like, you go to a point before where you had like options to choose, but you chose one direction. And then when you say backtrack, you remove, actually when you go to here, 1 2, you don't have a choice here, you had only one choice here. Are you guys able to see my pointer?
Yes, yes.
Okay. So you had when you go here, you didn't had an option, you didn't had like an options to choose, different options to choose. So you only had one option, which is 3, so you already chose that, so you don't have anything. So you backtrack to 1 where you had like, so but again, like you do the undo here. The undo is like you have removed the 3. So you, when you move back, you undo the 3 and move back to the option above. So that's the backtrack I call. Like you do an action and you undo that. That's how I usually identify, like, okay, this is backtracking way of doing that. So the two main things that we look at are uh, what is the bounding function, like on which conditions. Here we don't have many constraints. In the next problems, actually we'll look at like more constraints where you, based on which you stop exploring the paths and then you backtrack. Here we only had one condition where like you have to use all the numbers in the set. So you used all the numbers in the set, so that's when you start backtracking. So that's one point. The bounding conditions are one point on which you have to start the backtrack. That is one. And in general, the backtrack would be to undo what you have done before and go to a point where you had like, where you had chosen one of the options. So those are the two important things. So here, the bounding condition is like you have used all the numbers, so you backtrack. So in you backtrack, you remove 3, and then again you had already used all your options, so you backtrack again. So you go back here, and here you have chosen 2 here, and you had an option to choose 3 as well. So you go in this direction 3, and now you have done 3, so you come to the end. That's the reason I was using indexes, to make sure like once you reach 2, that is the bounding condition where you have used all the options. So the bounding condition is 2 here, right? So you use 2, so then you are done. Then again you backtrack. When you backtrack, you go back to the previous step. Then you chose 1 here, so you go to the next option 2, and then 3, and then in the same way. So this is the state space tree diagram, or I think some call it like solution tree, or state space tree is what is generally referred to as. So this is how you can represent. We can also look at, we'll also look at one more problem to understand more about the state space tree way of looking at this thing. Any questions on this one?
What is the condition that this is to indicate this is a solution? Like like for example, I'm go from empty to 1, and I need to add 1 into the solution. What the condition will say, okay, now the time to add 1 to the solution.
Here we want all the combinations, so everything is a solution.
I think limits would be 3. That is the point where you will stop one of the possible solutions, right? I mean the least part.
Yeah, I mean this 3 going to the index is when you stop and backtrack. But here for us, like we don't have more bounding conditions where we say like if the number of, we could also have like bounding conditions saying like the numbers in the set has to be only has to be at, at the minimum 2 numbers. Then we could have a condition saying that if the size of the set is 2 numbers, you add to the solution. But here the question is to find all the possible subsets, right? So everything becomes a solution here.
So even empty is a subset, right?
Yeah, empty is a subset. Yeah.
Okay, so every point in the graph, like in the tree, is a solution. Is what I would say.
Yeah. So Leon, here we don't have like a specific condition because we were trying to find all the subsets.
Okay, then what guarantee that we're not gonna include the duplicate?
We are not going to include. So here in this problem, what we have is like we are given non-repeating numbers. So are you asking about that or?
No, for example, I could have I could have add 1, 3, and later I could have add 3, 1. Kind of like that.
Here we are going forward. So if we had, so once we pick 1, we are not going backwards again, right? So we are only going forward. Like I choose 0, 1, 2, and now after here, I only go to the next number. I never go back. So how would?
Okay, yeah. So we go only one direction. That's
yeah, we only go.
That will make us not to add a duplicate.
Yep. Yep.
So even if
there is one problem.
I have a question.
Yeah. Yeah. Sure. Good.
Actually, here in the set there are only 3 elements. If the set has more elements like 50 elements and the 100 elements, so this same solution will work in that case also.
Yes, actually. So it's just like even if you have more, the number of options, the tree size, the practice in the tree will increase. So that should be fine.
Okay.
Are you talking about like a stack overflow kind of a thing? Like if it grows bigger because we are in the recursion?
Yeah, that can be a case also because like it's like a recursion problem also. And like if we talk about the time complexity of the backtracking solution, so what would be it like or we will discuss it later that.
In this case, these are like brute force kind of solution, right? It's 2 to the power of n. Everything is an option. All the options. We don't have any constraint to stop on which we are backtracking. So it's 2 to the power of n. I believe 1, 2, 3.
So yeah, that is correct, Naga. Like in the subsets are basically for n items, there are 2 to the power n subsets, right? For 3 items, there will be 8.
Yeah.
So for subsets, it's a direct to 1-to-1 relationship. Like for n items, there will be always 2 to the power n subsets.
Yeah.
So yeah, but I think the stack overflow may not happen here because remember we are not keeping entire thing in the stack space, right? So whenever we are reaching 1, 2, 3, then again we are coming back to 1, 2, and then the stack is again coming back to 1, and finally it is going to. So basically it is processing one branch at a time. So unless or until the depth of the tree is so high, then only we are going to get stack overflow. But even though there are 50 branches, like if we are thinking of a subset of 32, which is 2 to the power 32, around 4 billion, right? 2 billion, right? If we are thinking about positive numbers, then the depth will be going in that way, like in one branch, but not every branch will be at the time of the stack, right? I mean, it looks like in the picture that everything we're processing at the same time. Yeah. But if you think from a system perspective, it's a one branch at a time.
Yes, one branch at a time. That's right. Yeah, I'm still thinking if it will cause any stack overflow, but
in the stack it has to keep n elements, right? Like one.
Yeah, if your branch is let's say in this case, right? If we have 100, correct? Then we'll go 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, like this, right? Then whenever we reach it, there will be definitely
like a minimum of n. Yes.
Yeah.
Log of n, right?
Yeah.
It will be log of n.
It will be. Yeah, may not be log actually because this is not a balance, right? Right? Because log
would
means
be O of n, I think.
Yeah, exactly. It will be O of n. maximum will go to the O of n, right? Because this is not balanced, right? And also this can spread out n number of branches. So, but this is a linear, right? We have to go through linear from top to bottom. Yeah, this
Essentially,
is
will be
tricky.
O of height, and
Yes,
height
O of
has
height is nothing but, we are going through each and every item at each and every level of the tree, right? I mean, at least on the first node. If you think about the like the second item, then we are not really considering the first, right? We are only going n minus 1. Then for the nth item, we are only tracking only O of 1, which is the 3 in this case.
Yeah, right.
The
Yeah, it will be a little bit tricky actually.
Yeah, you're right. I think we are not storing all the tree every time, we are unwinding it. So the max is this one. And I think in the question they have a limit that they have provided.
For larger size, we can use bitmask then, right, rather than backtracking.
But if the question is to return all the subsets, then in any case we'll have to use storage space of 2 to the power n size, right?
Yeah, that of course
Yes,
we have
yes,
to do,
that is
because the result we have to return it in that way, right?
Yeah, the result
So
you'll
I
have to
think result may not be considered into the the storage complexity, right? Normally your computation plus storage will be calculated, but anyway you have to return the response, right?
Yeah, that's
Irrespective
not a
of
part
your algorithm.
Yeah, right.
That's a good point actually. Do we consider result storage as no? Because
Normally they do not, because if somebody is giving you, hey, can you please write the algorithm for me and return me the data, they already computed the storage, whatever they're expecting. But if you are taking more computation and storage, it is up to your cost, right? Because I know whenever I'm giving you, I am expecting, 2 to the power n. So I consider my storage cost. But within what is happening in the method, that is other person's API storage cost.
Yeah.
Right, that's not in our control.
Yeah.
Yeah, because okay, cool. That's a good discussion. Thanks, guys. So we have, I think, some of the questions that people raised. I believe the repeating numbers, and if you have to go back and all. I think I have the next problem. We will use that kind of an approach. So other than that, someone was talking about bitmask kind of way, like.
Yeah, I was saying, I mean, just to avoid the stack overflow, if there is, you can mask the bit of those many numbers, and then corresponding to each number, we can do the set bit. So in that case, you can avoid the chances of overflow, right?
Oh, use a okay. Use a bit instead of using the numbers here. You could use
Mask.
Yeah. I think that's good one.
That's good point. Yeah.
Yeah, but given that these are numbers, even if it is ASCII, anything you could do it, right? You just represent them and do that. Yeah.
Yeah, even if it is characters ABCD also, we can use that bitmask.
Yeah. That's true. You don't even care about storing all these numbers. Like once you have the solution, you use those bit masks to identify.
Yeah, so chances of overflow will be, I mean, totally vanished.
Yep, that's a good idea. Yep. So let's look at the code. So let's see the code in the like before I was just looking. They didn't give any conditions. Okay. So does anybody want to try out this code? I picked one templated approach, which was again shared on lead code discussions. So which we could apply for multiple kind of this problems. So have tried that templated approach for at least 3 or 4 problems, and that kind of worked. I haven't explored that with nqueens and nqueen and other ones, but we can discuss about that approach. Before that, does anybody want to try out this problem, or we can look at the code that I have and discuss about it?
Let's go with yours.
So there's one. I can share the link. There's somebody who actually discussed how to apply this kind of template for all backtracking problems. So okay. So it's pretty straightforward, like we did it in the state space tree. So this for loop is actually tracking the trees, each tree. So here we would have had a condition like what Leon was asking, like if we had some condition, we would have used that condition to put it to the result, which is output, where I'm creating the output. Sorry, I think I jumped ahead a bit. So given this function of numbers, I've created a recursion function, backtracking, where I have passed in output as the results, and each subset that I want to build as this one. And this is the start where I wanted to start. And this is the actual function. So when I come to this recursive function, the backtracking function, what we try to do is, like, in general, we would have had like an condition where we say like, okay, this is how I got the result, and then put the result only in those cases. But here we don't have any conditions. We wanted all the subsets, so we just put all of them here, and then we go into this into the loop of the tree that we were talking about. Like the first tree I talked about, like start with start with the 0th index, and then I kept on putting it until I get to the size, right? So I push the element and then backtrack, push the element, call back the function, push the element, call back the function. And once I reach the condition, which is the size here, then I pop the element and go back. So it is just exposing only the backtracking, not much of bonding functions. In the next problems, probably we can look at how we want to do those things. Any questions, guys? I believe this is one straightforward backtracking problem, not much of variation in it, but in the next problems there are some variations to it.
Yeah, this is fine.
So I was looking at this question. So this is an interesting solution you discussed about backtracking. I was doing it, not like using backtracking. I haven't finished the solution. I just started with it, but it seems a little. I don't know if anybody has tried it without backtracking. I was finding it. I was getting caught up in one of the steps, but. I don't know if anybody or you now that have tried without backtracking.
No, DP, but
okay.
Maybe I think we have. Yeah, I think the other variations of these problems are pretty similar. You may not need so much time. If you want, feel free to talk about it. Maybe we can quickly chat, like, because.
Yeah, I mean, I can talk about the approach, but my code is still, I have to debug. So I was thinking more like in backtracking, we went all the way to the, like it's a 3-element array, right? So we went all the way to the final set, like the longest one, and then we, took out elements, right?
Right. Let me put back my state space tree.
Sorry.
Let me put back my state space tree.
Yeah.
That kind of gave me a good idea. So yeah, sure. Go ahead in the meantime.
Yeah, so I was thinking, like, I started it with that. Okay, I know that given a set, I have like, element set, I would have 2 to the power of, 3 minus 1 subsets. So I started by saying, okay, give me all subsets with, like I started a counter for I equals 0 going till maximum number of subsets that are possible for this set, right? Which would be like what, 7?
Right? Yeah.
Including the empty one. So I started a loop which went from 0 till that number, and then said, okay, give me subsets with, let's say, empty, starting with empty, and then give me subsets which are you have at level 1 here, like 1 element set. And then I said, give me form subsets with 2 elements, and I was trying to generate this, subsets in that. set. I mean, this is what is getting tricky for me. Like in my code right now, I could generate this like 1, 2, 3, you know. When I start generating like 2 elements or 3 elements, right? Then I have to look at these combinations. Like if I start my counter at 1, then I have to say, okay, for 2 element subset, get me 1, 2, and 1, 3, right? So I'm missing this 1, 3. I'm getting 1, 2, and then 2, 3, but not 1, 3.
So you get one,
Not
one,
getting
two,
into the sorry, yeah.
you got 1, 2, and 2, 3, right?
Yeah, like I'm kind of, in my loops. I think I'm getting messed up.
But I believe, DP, your second pointer, right? One pointer starts at 1,
Yeah,
and one pointer will start at I plus 1.
I was
And
thinking
that,
of that. I was thinking of that, but then this case starts giving me issue, right? Like in this case, I'm starting my counter at 1, and then oh, you know what? You're right. Like even if I start the next counter at this,
yeah, so next counter will be there, and then that counter will be go till end. And once you go, you have to reset the counter.
yeah.
But the thing, it will be more trickier if you have more than 2, right? If you have 3, 4, 5 sizes, then you will have to maintain more pointers, right?
Yeah, that is another.
So that is always better to go with recursion in that case.
Yeah, recursion is the best.
Correct. No, that's true. Like if I have to do, thinking if I can do an abstract function like get next element, but it is getting like a little messier. Like this backtracking
Because
is.
you have to keep on trying all the combinations, right?
Yeah.
Like 1, 2, 1, 3, 1, 4, 1, 5,
Right.
then 2, 3, 2, 4, 2, 5. So the pointers will be in, actually. It will keep on going in. So again and again, yeah.
Yeah, I think there is another way of approaching this problem. I don't know that has been discussed here or not. But essentially at every step, what we are doing is we are doubling the already formed subsets, right? So if I can quickly annotate here, I'll show.
Yeah, I think you should be able to.
So initially, we have nothing. So the first thing we take is an empty subset. Okay. Now coming to this 1, what we do is we append 1 to the already formed subsets. So when I reach to 1, I already have this empty subset. So I simply append 1 here and I get this. Now coming to 2, I do the same. I append 2 to all the already formed subsets. So essentially at every level, I'm doubling my number of subsets. So now when I come to 2, I'll append 2 to the empty subset first. So this would be the outcome. And now appending 2 to this, this would be the outcome.
Yeah.
Now this would keep going on. So now I have 4 subsets. Now in the next stage, I'll have 8 subsets. I'll append 3 to the empty one first.
Yeah.
And this would like keep going on. Now 1, 3.
Yeah, this is also a good idea.
So this is the BFS approach, I think, right? We are going level by level.
Yeah.
It is BFS.
Yeah, BFS.
Yeah.
So this is also another
How would that be a BFS?
I mean, I don't know whether it's BFS or DFS. That we have to decide. But yeah,
because
level by
you
level,
are covering the level, right? Yeah.
Yeah.
So you are covering the breadth-wise, right? So in the DFS, we go to one branch and, in the recursion tree, and we come back, right? But in the BFS, we cover all the first levels, right? Basically, in this case, you are covering all individual items, right? Like, let's say there are 10. You are covering 1, 2, 3, 4, up to 10, right? Then once that is done, then you know that, hey, 1 is there in my queue, then pull the 1, and then you are adding to everything else, right? So yeah, I mean, it's kind of, visualizing in the tree way.
Yeah, so number of
but it will be tricky though, yeah, because we have to do a lot of bookkeeping, which
well, you can use
this
queue,
one,
right?
This one's a bit difficult to code than the backtracking one. Yeah,
correct.
Now, now I see that that it is BFS, right? If we use a BFS, it would be easier to code.
Yeah.
Because every
Will
time
depend.
we have whatever in the queue in that level, we have one level, and the next level we add a new
Exactly.
element to it.
Yes. Yes.
Yeah, sorry, this is Jan again here. If you call it BFS, what would be the graph?
I think
The graph will be, the root will contain, like 1, 2, 3, it will connect, and 1 will connect to 1, 2, 1, 3. Then 1, 2 will connect to 1, 2, 3. It's like, just reverse the, it's basically a DAG, right? Like if we think about the recursion tree, it's a cyclic graph, correct?
Okay.
There is no cycle, right?
But
Okay.
just think it as a level ordered traversal. So
Yeah.
it has nothing
Level
to do
order
with
traversal.
the graph or so, but you can use it in different ways, right?
Yeah, basically every tree sometimes is a DAG, right? Directed
Right, yeah.
cyclic graph, right? If we think about in that way, right?
I think they mentioned, somebody mentioned about that. It's called branch and bound method.
Okay.
It doesn't use backtracking. Yeah.
Branch and bond.
Branch and bound, yeah. I believe one challenge I see there is like you have to maintain the complete tree in the stack, right? So
You
here
have
we
to
are
put in the
combining.
queue actually. Yeah.
Yeah.
The label, right? Everything you have to put it. The first one you need to put 1, then you need to put 2, and then you need to dequeue from 1, right? First item, and then again you need to. By the time your queue will also contain 2, 3, 4, 5, right? So maximum 2 labels you have to put it in the data structure. It won't go beyond 2 labels because by the time you come to second level, you already 2 labels maximum you have to consider the size, and that you can find out like what is the n number of elements. So in this case, your first 2 will be n, right? And like basically every level it may not be those many elements also, right? Because it will be reducing. It's not a permutation; it's a subset, right? We are not considering other combinations. It's basically same element plus other, like 1, 2, 3, 2, 3, like this. We are only considering.
Yep. Actually, 2 levels have to be stored.
Yeah.
Okay. Good. That was a.
Thank you.
Yeah, I also wanted to add, like, not related to this one, but I think what approach DP was talking about, that reminded me one of the variation for this problem where you have been given a K, and K is you don't need to find all the subset, but you have to find a size K subset or the combination from the subset. So which goes as an input to the function, and then before you add into your the result list, you can check the temporary list size, and then you can add it to your result list. So that is one of the variation I've seen before.
And DP, if you look at the solution, it use your approach to solve the problem. So it use K at the size. So say if K equal 1, get me all the solution with size 1 and then size 2.
Actually that is what I was trying, like, get me all subsets of size 2 and then 3. But I was getting like my code was getting little confusing with, if I want to get all subsets in this one of size 2, then, to navigate this, like pick 1, 2, and 1, 3, and then 2, 3.
Yeah, take a look at the solution. They have that approach.
Okay, yeah, I'll check.
Cool.
Okay, DP, I think I am putting that solution, I think, kind of similar in the chat for later reference.
Okay, thank you.
Okay. Looks like the formatting is gone, but yes. Basically, I think that approach also work. You have to just make sure that you have to exchange your elements, swap elements, so that you don't have to do a lot of bookkeeping.
Yeah.
When you.
Yeah.
So yeah, I think
go ahead.
We can move.
Yeah, sure. Yeah, thank you.
Thanks, guys. That was a good discussion. I think we have learned.
Yeah, Naga, I just wanted to point out one more point which just came to my mind, that here we were dealing with the array, right? And if we do the same thing for the string, right? Like we have ABC as a string, and the same approach can be applied there, but in a different way, because string can be appended, and we don't have to take a backtracking approach there.
But you still have to remove the character from the string, right? So that you
It will be
finally
passed by, I mean, the string context within the recursion will remain of that length for that call stack. Maybe we are, I think it's going for the longer time. Maybe I can post the solution which I have, that because sometimes it gets confusing. It did for me once, finding all the subset for an array versus a string. So where string is passed by value, so you don't have to do a backtracking. You can just append to a string and work for that call stack.
Oh, okay. String is passed by value. The current subset that we are maintaining, you pass by value.
Yes. So
Okay.
I'm just posting my solution. Maybe if yeah, this is a. I mean, I have got confused earlier uh, between array and the string, so I explored a little bit. So I just posted a question with my solution. If anybody interested, we can.
Yeah, and I mean, even here, right, we are passing the vector as reference. So, but if we pass by value, I believe, I mean, like, if that works, this also should work then.
Yeah, you can make it a char. I mean, you can convert it to a char array, the string, and work it out in the same way. But you don't have to do a backtracking at that point. That's what my point was. Like if you directly work with empty string as an input and you keep on appending the next character, then also you can work through it.
Okay.
Yeah, but that would increase the function call space, no? Because pass by value creates another memory.
Yeah, that will be there. That will be there. But what I was stressing on is the context and the problem could be a little different. That's another variation. Like instead of array, you have been given a string. Definitely, we can solve with this approach as well.
No.
Right.
Good. I mean, anyway, so for today's backtracking thing, maybe
let's focus on backtracking.
Yeah. Okay, so one other variation of this problem is like I think when you have like repeated numbers, so the number is repeated. So in the first variation that we talked about, there was like no repeated numbers, right? So what would we do if there is a repeated number? So that's another variation. That's the only change. And the kind of approach works. It's just like our bounding function has like one new condition to it, right? Any ideas, guys, on like how we can solve it? I mean, like I've the solution that I have seen, they've done something which I'm not completely agreeing to. So any ideas on like how our solution can be modified to handle this repeated numbers?
But Naga, in case of backtracing, we haven't considered these elements, right? We are just playing with the indexes, right? So I think duplicates, it should give the same result.
Duplicates should give the same result. I think
because we did not compare numbers or anything, right? We just using the indexes, just moving forward.
So we'll have to skip that element which we have seen before.
Right. Yeah.
With the next number and the previous number, we'll just continue.
So maybe keep a set.
Yeah, in output maybe we can keep the set. Yeah, okay, you got it.
Or we can do the sorting of the input, and if the previous element is same as the current element, we can just don't continue the loop for the previous element. Sorry, current element.
Yeah, I think that's what I saw. But sorting the input is kind of not very good way, right? I mean, like you're given an input and you're changing the input.
We can use a set for output, maybe. That will remove, don't allow, that won't allow duplicates to come in.
Mm-hmm. So you mean to say in the output result?
Yeah, the output may be a set.
How does the output of this problem different than the previous one, even if it have a duplicate? Because it look, if we base on the index, like someone say before, it should be the same, right?
Actually, I think we can have here two twos, two independent twos. So just to make sure that that doesn't happen, I think set
How
should
would it
work.
not? How would we get another two?
Yeah, so Lian, actually, in this case, if we use the previous method, we will have a result set in that we have 1 comma 2 two times, because index 0 and 1 and index 0 and 2. So we have 1 comma 2 and 1 comma 2. But in the output set, we need only 1 comma 2.
Okay, yeah.
The repetition is don't
Also
be
number, yeah, same is number 2 is also counted, is only once.
yes, number 2.
So, but on the previous solution, we have the output is 6, right? This one we remove, we don't have duplicate, but the output is still 6. How could it be?
In the previous case, output is 8. I remember.
Oh, is that?
Yeah, it is 8.
Yeah, 8.
To
Yeah.
the power
8?
of n.
Okay.
It's 2 to the power of n subsets, right? So here we.
7, 8, yeah.
Yeah, I think both the solutions would work. I think one simple change that was done is like they sorted the input and removed the. In case of duplicates, it just ignored the duplicates.
Yeah.
Only
This
thing that
makes
I
much
was
sense.
not.
Yeah.
Yeah, only thing that I was not sure about is like sorting the input. That looked little odd for me, but. Yeah.
So we can maintain a set for that, I think, but it's more or less the same.
Yeah, set, we have to maintain two places. One is while, basically tracking the current number, as well as the output also need to be set, because, you can get two times. So unless we have, the output also is a set where we remove the duplicate, it won't be possible.
Okay, so output is set. That way, like we remove those duplicates.
Output is set, and the current what we are the cur, right? That also need to be set, so that also doesn't take care of duplicate both.
But
I'm
that
just saying that
remove two twos to only 1 2 here, right? It would make it 1 2 here.
Yeah, that is also a problem then. So yes, so I think it will be difficult to, yes, I agree. It will be difficult to do with just keeping set.
No, I think if we take the output as a set and then put that output content in a vector of vector, then we don't need to even use this condition, this duplicate one, nums of I equal to nums of I plus 1. Because as soon as that set sees an already present subset, it won't allow it to enter that set, right? So it will only maintain a set of unique subsets in the output.
So just make
you
this
don't
as
make current as a set. Yeah, just keep on
I
pushing
see.
it,
Okay.
and
Yeah,
then you can convert to
Yeah,
the
but the
output.
complexity will go up. I mean, that will be the same as the last one, right? With that.
Yeah, complexity would be
Space
that.
complexity is correct. Yeah.
Yeah, here we are.
We're not changing it algorithmically. Yeah.
Yeah. How to insert into.
Because that comes very quickly to your mind, right? So the sorting might be tricky to come in high stress environment. Yeah. So.
Yeah, I think keeping set is one way it is good, because you write a less code, there's a less chance to make a mistake.
Yeah.
For example, the line number 18, you can make a little mistake, and your output will be wrong.
Yeah, I think line number 18 is like just checking previous number is what it is saying. Okay, I made this as a set of vector, and then I'm inserting into that set. Let's see.
No, but you'll have to convert that back again when you're returning it. You have to convert the set into an eigenvector.
Oh, okay,
But if you use set, you will never get the 1 to 2 item in the list, in the output.
Yeah, I think that is correct.
Yeah.
Why?
No, you will get. You
No,
will
we
get.
will get
No.
it. We'll,
You will get 1 to 2.
So
Absolutely.
maybe
so
in C++ set allows duplicates or?
No.
No.
no, so
I mean,
here is the thing. See, I think I also made that mistake when I made first comment, right? If you convert the current CURR to set, then it won't allow 1 to 2. But when we are calculating the current one, we are not. We are just saying that do the last result basically, the previous problem, and then while just consolidating, we are saying that while calculating the output, we are just inserting that. If it is duplicate, it will overwrite or don't do anything.
Yeah, I think that would work, but it's just like we are, instead of not creating that subset, we are creating that subset and deduplicating.
Yeah, I agree. Yeah.
It's not.
Yeah,
The
exactly.
idea would have been like stop creating that subset instead of doing that. Yeah.
so one thing, I think we do not need, like
On
because
line 12, you will have to change to set again. Yeah.
Line number 12.
Yeah.
Quick
12
question.
you will have to set. Yeah.
Line number 12, we need to pass the set.
Output as set. Yeah.
Output is a set.
Yeah, quick question regarding set. So if you have integers, maybe it will remove the duplicates, but arrays and all, these are objects, right? Does it, remove these also? I'm just, I don't know. So
Because your
normally it
solution
will
has
check the
a
element.
signature change, right? So that won't accept. Lead code won't accept because of that. Yeah.
So set.
So you have no option to convert set to a vector.
At the end.
At the end, yeah.
Before return, basically.
Yes.
Okay.
But yeah, that is another question also. I'm not sure if C++ vector take care of, duplicating means really go through the value or some other way.
No, this should be fine because your set actually takes care of those if the vectors are duplicates.
I see.
Yeah. I believe so. It's like an element for it, right? So
yeah.
I'll quickly try once and then we can. I think it takes it like output.
Convert again.
Convert again.
I don't. Will that? Oh, okay.
Yeah, I think Pankaj put in the comment, basically. We have to do that. Return begin output and end output.
Yeah. Yeah, it did. It did convert.
Okay, cool. Yeah.
I think the only oh no. What was the difference?
Yeah,
so
all
empty 1 1 4 4.
Oh, 4 1 actually, yeah.
Yeah, they have all the last one.
Okay.
Oh no. What is happening is that if the order change, right?
Yeah,
for example, 4441 and 44. Yeah, so
that is a problem.
4414 and 4441 both it considered as duplicate.
Yeah. So in that case, again you keep a sort and then do it. Yeah.
No, then also it won't work. If you sort again, it is anyway duplicate, right?
So if you sort it, yeah, but then it won't. Yeah, it might.
No. So if you sort or not sort, right? 1 4 and 4 1, it won't be different. See,
I think that in the output, right? So why isn't there a 4? Because 4 is also a subset, right?
Yeah, it is there. It is there. Last third.
It is there.
Yeah, it is there.
It is in the after that. Yes.
Okay.
Yeah, but if you sort, before the backtrack.
Oh yeah, understood. I think we have to sort before inserting.
Yeah. So if you sort, then it might work. You just uncomment that sort on line 17, then it might work. 7, yeah.
If you are doing sorting, then I think it's better to do sort than every time all result do sort.
Yeah. Instead of recreate. Yeah. Okay. Like sorting the input seems to be the only way. Yep. But
That would be the best case, I think, sorting the input rather than sorting everything.
Yeah, sorting the input and then using that line number 19, condition.
That way we are doing n log n, there we are doing 2n log of 2n.
Yeah, because we are getting everything right before inserting.
Like all the subsets.
All the
bar
subsets.
n.
Yep. Okay.
I have, let's say, like go back to the original solution, right? We on line 19, we skip the duplicate, then how could the output we still get 1, 2, 2? Can you go click on the back to the description? Yeah, we try to see if we skip the duplicate, then how do we get 1, 2, 2 in the output?
Yeah, I also had that question, Naga. Like, if we skip the duplicates, how do we get the repeated element in the output?
Sorry, one moment.
Because you're backtracking, right? So every time.
Okay. Okay, so you're asking like how would we get 1, 2, 2, right? So we started with 1, and then we in the tree we got to 2, and then you had 2 options. So you try to add 1 to 2. The nems and nems minus 1 is equal to 2. Then we don't push into that at all, right? Sorry guys, maybe we can just try a quick thing here.
That's okay. Yeah, that's fine.
Yeah. So we came here, and the first option to the output is empty 1, and now you got 2. You did a 2, and now you get another 2. So skip.
Yeah, so the DFS approach, right? Yeah. So it is happened in the last 2. Yeah.
So here it got 1, 2, 2.
Because it took the previous 1, 2, and then it just added the index 1, 2.
So did it continue or?
No, it didn't. Okay. So try this one. Okay, so the current has 1. Now the current has 2. If you guys are following here, so one is empty, one is 1, and now we are building the next subset, which is 1 to 2 here. That would be 1 to 2. So we pushed 2 into this one. 1 to 2 is pushed, and now the index is 2, which is like 2, and the current is 1, 2. So now I is 2. Okay, so here I is 2 and the index is 2. It should continue actually. Nums dot 2 and nums dot 1 are equal. It should go back
No,
into.
but the first condition is not right, right? 2 is not greater than 2. The I is not greater than index at this point.
Yes, this condition did not meet. That is true. That condition did not meet, but I'm trying to visualize in the branch and bound. Sorry, in the tree. Uh, that's interesting.
So I think Naga, that 2 is
No,
coming next iteration, not
yeah,
same iteration. And we are avoiding to have 1, 2, 2 again. That's it. In the same iteration. Can I give an example?
so yeah, this condition will come into picture when we have encountered double 2 and then 1, 2 and 1, 2 again.
This condition will. Okay.
Yeah, I think it is something like you have moved ahead in the array, but your index is like you have moved ahead in the array. I think where the I has increased, but not the index, right? In recursive call, something like that. I'm not sure.
Yeah. So the I greater than index plays an important role there, right?
Yes, yes. So what I was trying to do is like, if you look at, let me share. Just let me share back the.
So I was. Do you want? I can add something here.
Sure.
Okay, you have something. Okay.
Yeah, yeah. So I was just looking at 1, 2, 2, right? So if we have.
Yeah, we'll assume the last 3 as 2. Yeah.
As 2. So we had like 1, and then we got 1, 2, and then again we went to 1, 2, and we picked the next index 2. But when we pick the next index 2, if you are checking that condition, wouldn't that fail here? Is what I was.
So we are checking the first condition also, right? And that is the I greater than index.
Yeah.
That is because of that we basically go through whole at once.
Oh, okay. Now here we have this option. We are trying to add index 2 here. And when we check that index 2 here,
it's not greater.
Yeah, but why would we even need the other condition, right? So if you look at, so if as long as when would we even hit the second condition in the if?
Because we are in the same iteration, but index is.
Yeah. When you go to again, and when 1, 2 and 1, 2, that time we will hit that because we are considering 1, 2 only once. If you continue that loop where you're debugging, we'll see that.
Oops, I
Yeah.
don't think.
No, that's fine. Even we'll go back again, right? Yeah.
Right.
Yeah.
Is it, okay. So here we have.
Now it will put 1, 2.
So we had I and index 0. So now we need to have index as 1 and index as 2 and I as 2. No. Okay. No, index as 2 and I as 2. Index as 0, I as 1 doesn't work. You want index as 1 and I as 2 or the other way? Yep. I don't think it even got to that condition ever.
No, it went right once. It just
went?
continued to, yeah, it went to the continue.
Okay.
Yeah, if you remove that, it won't work, I guess.
Yeah.
Okay, sure. I mean, like, I think I'll go ahead with this then. I'll probably debug later. Okay.
Asim, you wanted to show something, or it is fine?
I was trying to say like that would come in the next iteration. Like if 1, 2, 2 is coming in the next iteration.
Okay.
I see.
I think what Naga showed, the previous tree, that would be helpful.
Yeah.
Yeah.
If you want,
I
mean, if you want to understand, we can do all 1, 1, 1 and do, but I think it is fine.
All as 1, 1, 1.
Yeah. I'm saying that now, if you debug, we might understand that.
Yeah, I mean, I think I'm fine. I think I got the idea. I'll probably have to spend a little bit of more time.
Yeah.
But if anybody wants it, then we can spend some time. Otherwise, I'm fine going forward.
Yeah, we can.
Yeah, that's fine. We can move forward. I mean, like, this is not as trivial, right? It requires deep understanding what it do, on the deepest level. And when they come back, that will see, okay, this is duplicate, so skip this iteration.
Yes, I think it's not as like we look at it like we want to skip it when there is repeated numbers in sequence, but it's tracking more in the iterations wise actually. Yep. It is not trivial. You're right. Okay, so let's move on to the next question. So the next one is also similar, but here we have a little bit of more bounding conditions where what we want is we want to pick the candidates whose target sum is exactly a number 7. And here the condition is find all unique combinations, and the given conditions are without duplicates, and one more condition is same repeated number may be chosen. So I think, Leon, like the way you were asking, right? We were going only forward in the earlier condition, but here what they're asking is you're fine if you want to choose the same repeated number again. So that's an interesting twist in this one. I think there is one more problem without using that. We can look at that one, but just to add some flavor to it, you can choose the same number is a condition here.
So this thing can be asked in a different version, in a like a real world problem, and I think people are familiar with either baseball or cricket. You can make you can take 4 runs, 6 runs, or you can take 1, 2, 3. Now you have to achieve a target of 20. How many different ways a player could make a target 20?
Oh, okay. Yeah.
So there could be different. I can take first 4 runs, then 6 runs, then again I can take 4 and 6, or I can take all 1, 1, 1 runs, or I can take 2, 2, 2, 1, 2. So like that end up with this problem only. Like if you find like somebody asking that problem in a game type structure, that would end up like this. Or it could be like you have different money. You have coins of 5 cent, 10 cent, nickels, dime, quarters, or then how you will, what are different ways you can make this sum.
Yeah. But I think
the coin change problem, right? Almost.
Yeah, but here the difference is we don't have to give the number different ways, but we have to give actual sequences.
Mhm.
Yeah, actual sequences. But again, I think here it is like you're given like limited denominations or limited ways of making those, right?
Yeah,
You
that
can
would.
runs, you can make any runs, but if they say like you
No,
can only make 2s, 4, and 6, then that
yeah,
would.
then that would become our limited line. I can take 1 run, 2 run, 3 runs, 4 or 6. That's it.
That's it.
Now
Yeah.
I have to make a target of 100.
Yeah, yeah. When you're given a limited set of denominations. Yeah.
Yeah. Like in any game, I think there's only like I took a cricket example. We can only take 1, 2, 3, or 4 or 6. There could not be any other way to score run, or might be there, but yeah, you like you're right.
Right.
Uh,
Yep. Yep. Yep.
I think the other way to look at this, like similar to the coin change problem, we have this amount, and how many way combination of coin we can sum add to this amount. That's similar, right?
Yep. That's
yeah.
Yeah.
But as Asim said, I think that's a number of ways, because I was also relating this to like unbounded knapsack, which we did some time back, where you can pick the same element multiple times to get to a target, right? Where it's a category of unbounded knapsack where we did with the DP, right? But that was for the
Number of ways.
number of ways actually.
But here we have to give the actual. So here we can't use like DP because otherwise we can't able to give like how many. There we can reuse actually, but
Yeah, I
here
think we can reuse. I mean, we have to rethink through that when we make that 2D array, or like see, if we can reuse that. I'm not sure how. We have to try that.
Yeah. One difference from what I have read, they say is like DP versus this is DP. You always try to find an optimized solution. So your thinking is more in terms of like finding the optimized solutions and use that. Here it is like all the combinations, all possible ways of doing it.
Yes.
Yeah, given the bounding conditions.
Yeah.
So even there, you try to find all possible combinations, but you try to optimize it by using the existing by using the existing solutions from the sub problems, right? Here the goal is to find everything, so you don't want to try solve like the smaller problems first and use them later.
Right. Right.
In DP, like because you know that trying to solve sub problems will give you an solution, so you try to do it in that way.
Right. Right. Yeah, that was
Problems.
one of the criteria, like for the DP, where you try to maximize or minimize. That is one of the base criteria, I think, for DP problems.
so this problem, if I say don't give me these 7, 2, 2, 3 list, if I only say give me ways, I think that will become a DP problem.
It's not necessarily like maximize and minimize, right? Like if I look at the Fibonacci DB problem, there's no maximize or minimize. We just like, remember the previous solution and add them up. So I think this case is same as that.
No, I think the way you started in Fibonacci is like you started with smaller problems so that you can store them and reuse them, right?
Yeah, but there's no minimize or maximize,
Yeah, not
sub
trying.
problem.
That is true. It's not like you're trying to find an optimized solution. There also you're trying to find a final solution, but you're using sub problems. You're using like solution that came from the smaller subset of. You're trying to find the Fibonacci number of a smaller numbers and use them when you're trying to find for the bigger one. Here I don't think we are doing like we're trying to find one way or the other way. Like we want to find all, so we go top down. That's what I heard.
Yeah, I think that will be interesting actually to try this out with the TP. Like, can we fit in finding all the combinations? I mean, that will be a separate thing to try it out. But
That's what I'm talking about. This is same at the coin change that also use a DP. you know, it only like the wording is different, but that's the same.
But here we have to give the actual pattern. So that is the difference. You're not giving the ways.
You have to give all the combinations.
Yeah, but like remember on the coin chain we have like, you know, denomination and we have the amount and how many way, you know, we can how many way we can add up to this amount.
Yeah, if the
So
problem
think of up 2, 3, like, you know, a coin of 5, 10, or 25, and you have, you know, 100. The target's 100. How many way you can get to 100?
Yeah, I think if the question is like how many ways, then it's the same problem, right? But if the question is like to use the minimum number of coins and make the denomination, I think then that becomes a different kind of problem.
I think we're talking three problems here. One is like minimum coins to make a target. Other one is if you have given points and a target, what are the ways? And third one is this one, where you actually tell like what exactly I would going to be doing. I'm not giving you a number like, oh, there are 10 ways, but I'm also telling you what are the 10 different things you are doing.
Yes.
Yeah, right. Yeah.
So that's make this problem different from the two other.
Right.
Okay. Yeah. Looks like I think we pretty much understood the problem. I think we're looking at different variations and all.
Yeah. But I mean that is the main thing, Naga, because I've been struggling with this earlier, that if you see a different problem, like we think differently, but they fall in the same category actually.
Yep.
Yeah.
I mean, I felt like the at least like the coin change problem to try and find use the minimum number of coins to find to get to a certain denomination. I felt that's clearly like a DP kind of a problem, right?
Yeah, that's a different problem altogether. Yeah.
When you look at it like find all kinds of combinations, then it becomes a different problem. Like because there is nothing that you can optimize it, right? You have to find all the combinations.
Yeah, but Naga, here this problem also, if I tell you just give me ways, then we can reuse something. Even I think in this problem also, if we try to reuse, the problem is if I want to do some kind of memoization, but the problem is how I will do it, because we are talking about objects here, like there's a list 7, then 2 to 3. So, but there is another question, I think combinational sum 4, which talks about similar thing. Like you have to give ways, and there they have used memoization rather than solving everything from scratch.
Oh, so even finding the combination, they've used memoization.
Yeah, ways, only ways. That's what I'm telling.
Oh, okay.
Because there you can use, because you are treating you are tracking a number, not an entire list. Like
Here
when
also
you
we can use memoization, I think.
we can use memorization here, but it would be really tricky. Like you have to convert your list to a string or whatever and see like, oh, I have seen this thing earlier. Because
Okay, I was thinking of using a 2D array where I'll have two states. One would be the index in my given input, and the other would be the target. So on that basis, I can use a memo.
Use the memoization here.
I think let's Naga proceed with his solution, and then we can.
Yeah. So even for this, I've looked at the state space tree and similar kind of approach that we have taken before. Maybe we can look at it. I don't know. Looks like memoization might be possible, but I cannot think of it as of now. So let's see. So I believe like the question is clear, right? Yes, I believe. Anyone has any questions on the problem, given problem? Okay, let me share the state space tree. Okay, so I didn't draw the complete one. I've just because it becomes pretty big. So here again, like going by the way of like looking at the options and checking if the condition is met or not. Earlier, like we don't have a condition, like we were discussing, right? We are putting everything into the result. Here we have a specific condition when we should consider that as a result. Earlier, like we are trying to find every subset thing. Here we have two conditions. One is the total sum has to be 7. Only then that becomes a result. And here we could also use repeated numbers. Earlier, one of the questions that Leon asked was like, we are only going forward, but here we could always use the same number again. So those are the two extra conditions. So then that makes the tree bit interesting. So first time you have an option to choose one number, you choose that option, but it did not meet your bounding condition, which is like the sum has to be 7. So now you have 5. So you can choose 2 again. So I've chosen 2 again, and the sum became like the total, the target is now 3. Then I choose 2 again. Then I still have an option 1. So I choose one more 2 again. Now the condition did not meet because the number went above. So this is where I can start backtracking to a place where I have chosen the option, right? So I go back here and I then remove the number from the set that I created. And here I have already chosen 2, which is my current, which I could repeat. Then I choose 3, and then it did not meet. So I break from here. These are like cross marks, so I break from here and then go back. I've chosen 3, but I still had other options like choose 6 and 7. So I tried all of those things, it did not. So then again I backtrack to previous step, which is like 2, 2, 3, and I've chosen 3 and the sum is 0, and this I'll save it in the result. So converting from what we have done earlier to this one, so we were using this condition to make it, only difference is like we were using the condition to make add to the result, and also we were, instead of going to the next next index always, we were actually using the same index until we break or until we get to the end of the input. So I've written only for couple of the nodes, but the idea is the bounding function and how we use the number. Any questions on this, guys? I think we can talk about memorization, like how we can use the memorization here to make it more optimized, but just extending the idea that we talked about earlier using the state space tree and the bounding function. Any questions on that? Cool.
No, the picture looked pretty clear. Thank you.
Yep, thank you. Yeah, I think it's a standard state space tree. So I believe we can talk about memorization a bit and look at the code. So I think the Asim, so the memorization that you are talking about is like storing these sets, right?
Yeah. So let's say like when you came with 6, you're again at the top of your tree.
Mm-hmm.
Yeah, second level. When you're coming with 6, I'm just going a little far ahead because again you are going to compute 2, 3 with some different passing a different sum. So you will pass 1 that time, correct?
This
When you are
one,
at 6, yeah, you will again start with 2.
here,
So
Yes,
that
yes.
so what would be our next take that time? We would be sending something like we would be here. We are trying to send 1 to that 2 because we are again starting the loop, right?
Mm-hmm.
So if I have already computed 1 in some other iteration, I would be knowing like what path it would be going in. Like say something down the line, it gives me some result like 0, 0. So basically, I knew that if I send 1 again to this guy in the so basically we are again starting with 0th index. So that means I know what is the result.
Why we need to start at 0 index?
That's the algorithm. Every time we start with 0th index. So this is 0. This is 0. This is 0. Correct me, Naga, if I'm wrong.
Yeah, we could repeat the number actually.
Yeah, we can repeat the number. So every time we start with 0.
But here it's like.
So I think everywhere we start with 0 first, right? And again repeat the entire thing. Only difference is I'm passing 1 here. So see here, I'm passing a 1 here. And here also I'm passing a 1.
No, Asim, here actually that we cannot do because we cannot repeat the same thing again. I mean, like you can repeat the number, but you cannot repeat the combination again.
We are not repeating because some value is different. It will end up in some other combination.
No, but if you start using 2 here, that would become like 2, 3, 6, right?
So, okay, let's take this example, Naga. I'm just drawing here. Sorry, I'm spoiling everything. So this is one example where again 1 came and we started with this. What would happen here if I send 1? Would it be the same thing?
On 6 1 or?
On 6, when 6 will go to next level. Would that end up?
It would be the same thing, right? 6 2 and 2 6 would be the same.
Yeah, that's why I'm thinking we don't need to start at 0 again because
we
you think about when we start at 0, we already include 3, 6, 7.
Yep.
Right now, if we start at 6, we don't need to include 2 and 3 because we already processed that.
Yeah. You could repeat the number, but you cannot go back. That would make like a duplicate subset.
We can repeat a number and we
actually I don't think we are going back. What's happening here is we are storing the current sum. So what we want is 7. So out of 7 we have got 6, and we are looking at the combination in the way that we 1 is left. So in how many ways I can get 1? Previously, if I have got 1, we are looking for that in memorization. I think so.
Okay, go ahead. Sorry.
So I think that's what you're trying to say, correct? Yeah. If we have some previous combination which gives me a result for only 1, sum as 1, that's what we're trying to get here, right? We have got 6, but have we got 1 earlier so that we get a combination of 7?
With the previous numbers.
Yeah, with the previous number. Yeah, please carry on. Yeah.
Okay, got it in that way.
But that would become. Okay.
Yeah.
So you'll have to save all the combination numbers and then try to append this. So in this case, like you have 6 here and like you want 1. So you try and find if there is a 2 2 2 if there is any combination which is making 1 and append it here.
Correct. Yeah, that would be one of my answer.
No, but that would be, but that would be the duplicate work, right? Like Naga say, before you already have, supposed to have a 2, 6, and now you're going to process again 6 and 2.
So I think I got it. What we are doing, we are sending the sum plus index, right, Naga?
Yep, the sum plus index.
Okay, so then the combination would be like the unique factor is sum plus index. If we have seen that sum plus index earlier, we don't need to go that path. So I think the unique thing here is sum plus index. So my bad, I thought we are repeating things again, but then this guy will factor. So if I'm going to next level with the same sum plus index, that means I should not go in that path because I already computed that.
Yeah. Yeah.
Why plus?
Not plus, I was trying to concatenate.
And
Okay, you mean sum comma index, right? These two states.
Yeah. Two states.
Okay.
And the output of this memo should be a vector, right?
Yeah, output should be a kind of a vector.
Right, because in that previous question where we are asked to find the number of ways, there we have that simple integer denoting the number of ways. Here we have to keep we have to keep the vector so that we can reuse it.
Mm-hmm. So if we can maintain something like this, I think that's doable.
Mm-hmm. Then again, we also
to
have
give a
to.
quick, okay, yeah, please,
Go
please.
ahead, Ash. Yeah.
So just to give one clear picture, so we'll have a memorization from 0 to 7, something like that. And for each sum, for 0, we'll have all the combinations which will make 0. For 1, we'll have all the combinations which will make 1. So that's basically a part of DP only. So we'll have two attributes to store. One will be, just for example, if the sum is 2, the attributes will be, by using which all subsets you got the sum to. So that all we have to store. That will be quite complex actually, the memorization thing. But
Because we also
can be implemented.
Mm-hmm. Okay.
Actually, in case of memorization, we need to store the list at every
Yes.
index of our, you can say the means whatever we are keeping in the array. So for the space complexity wise, it will be huge, right?
Yes. So yeah, but instead of a vec, if we have to keep just a ways, then it would be simple.
Yeah. So just a ways, it will be simple and it will be effective. But if we keep the list and all the combination at every location, then space complexity will be huge.
But the idea
Sometimes,
is like if I have at some point some like 7, and let's say we make that to string, and then plus let's make we were having some index starting with 1. So whatever we computed that time, we don't have to do it again. If this is my key or whatever, like we are maintaining this 2 states or something like that. Yeah. So what I was trying to say, like, let's make some more things. Like we're doing 7,1, and this was my list, like 2, 2 or 1. So we don't want to go, but like somebody correctly pointed out, this would make our space like really crazy.
Would you be using memorization with the backtracking solution or with some kind of or some recurrence solution?
It depends. We can do backtracking and not. If you're sending a new list every time to a next state, then you don't need backtracking.
Okay, because if you use backtracking and memorization, that key sum plus index only occurs once. You never find the key again.
We won't find the key.
Yeah, the same key sum plus index only happens once during the backtracking.
Yeah, in backtracking, I think we won't be requiring memorization. Just for the recursive and the DP approach,
Right,
will require
the recursive,
memorization.
yes, right.
Interesting.
Yeah, backtracking is anyway exploring all the paths. So
Yeah, we are exploring.
Yeah, exactly.
But I thought, like, while exploring all the paths, I thought we could bound it by using memorization. Like if there is a sum that we need to find, instead of going forward in the tree, I thought we would use some existing memorization.
that is what like you do in DPA, right?
But here we have the sum plus the index, and that happens only once during the backtracking.
That will never happen, so we don't even have to.
Right.
Yeah.
Let's see, even if we have the memorization, because the number could repeat multiple times, right? So we still need to do a lot of work. So that's similar to backtracking then, because, otherwise how could we do it faster if the number could repeat multiple times?
So one question. So what we are doing is that the first level, the childrens are 2, 3, 6, 7, right? And 2's children are again combination of 2, 3, 6, 7. Is that correct?
2's combination of?
So first 2, the child of that node is again 2, 3, 6, 7. Basically, we include 2, we include 3, we include 6, and we include 7.
Yep.
Right. But
yep.
the third 3 in the second row, its children are doesn't include 2, right? It is either 3, 6, and 7.
Yeah, 3 could repeat, but 3,
yeah,
6,
but
7,
yeah. So that way, 6 children are again 6 and 7.
Yes.
Right. So whatever we are discussing, saying that memorize and something, right? Even if we don't do it, we can take care in the optimal way, because we are not going to repeat that, right? See, what we are saying is that, okay, 6 means we need a 1 as a target.
Right.
And we see if the 1 came before or not.
Mm-hmm.
If the one came before, that means that result is already explored. We don't even need to go further, right? In a sense, the one where the solution that includes the 1 from the previous and also include the 6 would have come into that tree path actually when we are exploring
that's
that.
right. Yeah.
So I mean, I don't think so. We are generating a duplicate here in any case, right?
Yes, that's right. I think that's where it came to, like, when you're using backtracking in this way, there's no need of memorization. Never it would repeat actually.
Yeah, it would never repeat, exactly.
Yeah, indexes and some would never repeat it. Yeah, I think someone was pointing out that. That's
if there is a variation of a question, if it can repeat.
Yeah. The other it duplicates if having the like having 2, 3 and 3, 2 is allowed. I mean, like in the indexes, if the reverse of the number is allowed, then that would make sense.
I think, sorry for that, I got confused with that. So the example which I gave in the start, the cricket one, holds only true if you can repeat the pattern.
Yeah. I think you also started in the same way, assuming that you could also use 2 when you went to 6. That's right, actually. I think the question is, like, you could repeat the number by itself multiple times, but not the other one. I think when I explained it also, I didn't explain it in a proper way. Because that's right. That kind of clarifies.
And other thing is that the moment we are going negative, we can cut down that tree. We don't have to go further, right? For example.
Yes.
So,
I think that's
even
but
so we don't need to even find 4 children. So first children, if it is negative, then if the input is sorted, or we can sort it, then we don't even have to explore that further. For example, in the last, right, 2 to 2, and then we need 1. Now we take the first element, that is 2, and that goes into negative. That means we don't even need to go further 3, 6, and 7. We just cut down that.
I think that's bonding function. Yep.
Yeah.
Okay. Bonding function.
So, what if there is 1? So in the
no, I'm saying that we have if the input is sorted.
Oh, okay.
Yeah. So in that case, 1 would have come first. Yes.
Yeah. So I think the concept here is pruning. We're pruning the tree. Whenever we reached something that's not possible, we prune that branch.
Yeah. To just make it more efficient. Yes.
Good. I think that was a good discussion. Any other ideas or any other questions, guys? We can look at the code. I think it's again in the same template that we used for the first one, except that earlier we don't have bonding functions. We have bonding functions now here, so we can look at that.
What is the complexity? Just wondering.
I think for all these things, the complexity is since we could repeat the number, 2 to the power of n was like without repeating the number, right? Because now you could repeat the number, it is like n into 2 to the power of n.
Like, okay, if I have to drive a complexity from here, so we are opening how many states from the root? 3 states. And then every time we are adding one more state.
So n, it is like, if you look at simple, all the combinations, it is 2 to the power of n, right? So like, but every state we are allowed to repeat. So this could go like multiple times. So in every combination, you could have that thing repeated. So if you don't repeat it, you would not have this tree, this complete tree at all.
Mm-hmm.
But since you are allowed to repeat, this could go until the sum. I mean, like, because we have a bonding function, it is best case is not n into, but worst case could be
One
n.
and like
Yeah.
whatever sum we require into 2 power n.
So worst case, if we found, suppose all are 1, right?
Yeah,
and
yeah.
Our target is 5. That means we are going to explore all t and not found the result. Basically, that's the worst case.
Exactly. So 5 into 2 power n, I think so. Might be the worst case.
And zero be the one of, and zero be one of the input. If zero there, then we could like repeat it forever, right?
That's a good question. If zero is input, that's a good question. I think.
Or if it's zero there, we have to search it and remove it.
Yeah, I think in the input.
Let's see question. Does it says that it is positive integer and not 0? Because if 0 is there, then we can just simply ignore it.
Yeah.
0 is not going to change anything. But that's a good point. Yeah.
Yeah, that's a good point. I think they did say that they.
Because 0 doesn't make sense in any
Yes,
way, right?
yes, that's right. They gave like less than or equal to, greater than or equal to 1.
Yeah. Okay. So that makes sense.
That's a good point, Leon. Yep. 0 will make it completely. Yeah. Okay. So let me let's quickly look at the solution. It's again using the same templated way, so it makes it pretty straightforward. So this is combination sum, and it also has a variation actually with without repeating. So that's also good. Okay. So yeah, we can look at the solution, I believe. So if you look at the difference from earlier, so we had this two bonding. The bonding function was if the target, because we have the target as like reducing the target in the repetition, right? Until here it's the same subset we want to build, the result, the overall result that we want to send, and the candidates, the input and the target sum is passed to it. And whenever the target is less, then we don't have to proceed further. So we just return. And whenever the target is 0, that means like the current subset that we have built so far is the one that we wanted. And same thing, like we are trying to push the numbers into the list. And we backtrack and we pop here. What we are doing is like we are passing the number again. So here we are not proceeding further so that we could repeat the index, right? We started with 0, but we are passing the 0 again and again, whatever the input that we got. So again, it followed the same template. It's just that we had this bounding functions, I think.
So we don't increment the index here, but the I increment is what is taking care of, because in the previous, I think solution, we were incrementing the index in the recursive call, right?
Yeah.
Yeah.
Here we are. Yeah. I think if you don't want to repeat the number, we just have to increment it so that we will not take the same number. Now that's the next variation of the question, but
got it.
So on
we don't sort the input. We don't
we
need to sort the input.
Yeah. Yeah,
go ahead.
Yeah. We don't need to sort the input from what I have seen. In this case specifically, like there's a next variation where we had to sort.
I think in this case we are not sorting because we are not also, if you see, we thought that, we would cut down the for loop if the number are going negative. Here we are blindly going into the for loop, and the call back. I mean, sorry, the call to the backtrack will basically return if it is less than 0. But suppose the first index is 0, still we go through all the numbers, so we don't need to sort actually. For example, line 29 is at at the line 36. Basically, before pushing and backtrack, we want to see if we are reaching the negative, then we don't want to even call, right? We don't even backtrack, and we want to cut down the current for loop also going further. Then in that case, we need a sorted number. But I think this is also fine. We are doing a little bit extra, but that is fine.
If it was sorted, we would have.
Yeah, we can cut down that, right? We, instead of calling backtrack and then check whether target is less than 0, before calling that, we say that target minus condition I is less than, it is greater than 0, then only call. Otherwise, don't even call.
Yeah.
Yep.
It's like a minor trick which can reduce the complexity.
Yeah, little bit. But I think this is fine. But yes, so in that case, we need sorted if we want to do that. Otherwise, it's fine.
Okay. So let's we just have like a couple of
minutes. I actually don't think it would reduce the complexity, right? Because we're talking about asymptotic complexity.
Yeah.
And adding I don't think it would reduce the complexity.
So yes, algorithm complexity will not be reduced if it will run efficiently if there is depending on the input. But overall complexity, if you say that how much it runs, that stays same.
That still says same, n into 2 to n2 to the power of n. Yeah. That will still say the same, but we would avoid some conditional checks.
See, it is a little bit more efficient in some input, and it doesn't affect adversely for the bad input. That's the only advantage we get.
So if we put the condition, we're gonna put it in, at the for condition, right?
No, I think before we even enter here, I would put a condition here saying that if the target minus
so at line 36, right, before even pushing and calling the backtrack, we can put that condition. If target is less than 0, don't even call back.
Yes.
Or I think
continue from here.
And in fact, break the for loop that place. If target is equal to or greater than 0. I mean, less than 0, then break the for loop. Sorry.
Okay.
Yeah, I think you plan to look at the number 2 also, right?
Yeah. Just a variation because we discussed this, so that variation would help actually. So here, what they're saying is like you don't repeat the condition. Earlier, it was like you don't repeat the number in the candidates. So earlier we are repeating, right? So here we don't want to repeat. So to avoid that repeat.
So you can repeat it if the number is repeated in the input, but same index you cannot use twice.
In the earlier case, we were using the index twice.
Yeah. So in this case, I'm saying that, see, here number 11 is repeated, so you can use 2 times if you want. in the input itself, but but you cannot use like 3 or 4 times 1 because it's only 2 times repeated.
Yeah, and earlier case we were having the condition that they are all unique. Actually, there is no repetition there. You could repeat. Yeah, here it is like the number is repeated and you don't use the same index again. You have repeated numbers in the candidates and you don't repeat. Yeah, I think that again the whatever we tried earlier, like removing the duplicates and sorting it, is all same. Again, since we don't want to repeat the index, we are moving forward in every call to the recursion.
Would you mind showing the previous solution to the previous problem?
Yeah.
Okay. Thank you.
I felt like this, I picked it from some template. Felt like this kind of backtracking approach should work for most of the backtracking solutions. I haven't tried for the NQueens and all this stuff, but yeah, found it interesting. So I think we are almost time. There is one question that was there, but it's again the similar thing from Tech Delight. So let me see if we have it. It's again same, but the bounding conditions are different, saying that find all the combination of elements where it only appears, a number only appears twice and the distance between them is as the number. So it's just like a trick on how to make the bounding conditions. Otherwise the same kind of approach would work. So I'll let you guys take a look at it. I think they also have a solution here. I just tried to pick something out of lead code. So this was something interesting, but again, it's a combinations problem.
Yeah. Just to add to this, like I have seen this kind of problem earlier where Asim was also talking about with an example of like a game, right? Like you take an example of cricket or a football and how many ways you can achieve to a target. But if you take an example of a game like NFL, where for a touchdown of 0.7, after you make a 6 points, you can make a 1 point, right? So there are conditions that if you pick one number to pick the other number, there is certain conditions. You cannot take like after 6, you can or you cannot make 6 points. You can make 1 point, 2 point, or 3 point. Just as an example, I'm saying. So I think this seems like a similar variations to me, which is an extension of that kind of problem.
Yeah, I think the bounding functions are different, but the idea is all same. Pick the combinations based on the bounding functions and when to stop proceeding further and what you can pick. Two bounding functions. Yeah, that's what I kind of understood looking at these problems. Cool. Yep. Thanks, guys. I'll stop recording.
Cool. Thanks, Naga.
Yeah.
Thank you, Naga.
Thank you.
Thanks. Thank you very much.
Thanks, Naga. Hey, Naga, do you, so
I'm able to stop recording. Can you?
Yes, let me do that.